Hello students, I am Professor Sanjay Bhargava, MSc in Physics, PhD with a teaching experience of more than 38 years. In my first video lecture, we studied about basics of electrostatics, about charge, its properties, electrical force and so on. In this lecture, we would be first comparing the properties of electrostatic force and gravitational force. For that, we select an electron-proton system separated by a distance r. Here, electrostatic force between electron and proton is given by k, q, charge on the electron, charge on the proton upon r square. Similarly, gravitational force is given by equation g, mass of the electron, mass of the proton upon r square. Looking at this, there are certain similarities and differences between the two types of forces. First of all, what are the similarities? Both the forces obey inverse square law. Fe proportional to 1 upon r square. Similarly, Fg also proportional to 1 upon r square. Both the forces are central and conservative forces. If they are conservative, that means the work done by the force along a closed path would be equal to 0, or work done by the force will be path dependent. Both the forces can operate in vacuum. When the differences are concerned, then we can say gravitational force is always attractive, while electrostatic force can be attractive or repulsive depending upon the polarity of charges. Gravitational force is a medium independent force, while electrostatic force depends on the nature of medium. Electrostatic force is a very strong force as compared to the gravitational force. For understanding what we are saying, we take an electron-proton system. In the electron-proton system, we first calculate what is the gravitational force, g times mass of the electron, mass of the proton upon r square. Similarly, electrostatic force Fe would be equal to k, charge on electron, charge on proton upon r square. The ratio of the electrical force to the gravitational force is then equal to k times charge on electron, charge on proton, g times mass of electron and mass of proton. The value of the electrostatic constant is 9 into 10 raised to power 9. Similarly, charge on the electron is 1.6 into 10 raised to power minus 19 coulomb. Charge on the proton is also 1.6 into 10 raised to power minus 19 coulomb. The gravitational constant is 6.67 into 10 raised to power minus 11. Similarly, the mass of the electron would be 9.1 into 10 raised to power minus 31 kilogram. Similarly, mass of the proton is 1.67 into 10 raised to power minus 27 kilogram. On simplification, it gives 2.4 into 10 raised to power 39. Thus, electrical force is 10 raised to power 39 times the gravitational force, which justifies our saying that electrostatic forces are very strong as compared to the gravitational force. For electron-electron system, this ratio is 10 raised to power 42. For electron-proton system, we calculated the ratio as 10 raised to power 39. For proton-proton system, the ratio comes out to be 10 raised to power 36. All these examples substantiate our statement saying that electrostatic force is very strong as compared to the gravitational force. In our first video, we studied Coulomb's law. To check our understanding, let us take up an example. Coulomb's law is applicable basically to discrete independent charges. Here the question says, divide a charge capital Q such that force between the two parts is maximum. So let us say we divide the charge Q into small q and Q minus Q. Then the force between them would be equal to K, Q and Q minus Q upon R square. For any force to be maximum, the first derivative must be equal to 0. So dF by dQ must be equal to 0. So we can write K upon R square d by dQ of QQ upon minus Q square should be equal to 0. Differentiation, it gives Q minus twice Q must be equal to 0. that is charges Q must be equal to capital Q upon 2. For the force to be maximum, the charges must be divided into two equal charges. Then and then only the force between them will be maximum. Now the question comes up is, what would be the force between multiple charges or superposition principle? For this, we consider a system of charge here. We have a charge Q1 set at a distance R1 from the origin. We have a charge Q2 at a distance R2 from the origin. We have a charge Qn at a distance Rn from the origin. At the origin, we have a test charge Q0. So we say we consider a system of n charges Q1, Q2, Qn in a vacuum. We need to calculate what would be the force on test charge Q0 due to system of charges Q1, Q2 and Qn. According to superposition principle, the total force acting on the test charge Q0 due to system of charges is equal to the vector sum of forces exerted by the charges on Q0. So force on the test charge Q0 is force on Q0 due to Q1, force on Q0 due to Q2, force on Q0 due to Qn. While doing so, we have neglected the force between individual pair of charges like Q1, Q2. Why? We have already proved in video 1 that the sum of internal forces is always equal to 0. Substituting the values of Fq0, Q1, we write K Q0 Q1 upon R1 ka square, direction being given by R1 cap, K Q0 Q2 upon R2 ka square, the direction being given by R2 cap, K Q0 Qn upon Rn ka square, Rn cap. Simplification, it gives me a force must be equal to Q0 summation I is equal to 1 to n K Qi upon Ri ka square, Ri cap. This equation helps me to calculate the resultant force on the test charge Q0. How does the principle of superposition works? To check, we pick an example. We have a square of side A. So this represents a square of side A. 4 equal charges Q, Q, Q and Q are placed at the points A, B, C and D, that is the corners of the square. We have to find out what would be the force on charge Q placed at point C. Now, the charge at C would experience a force due to charge at D, charge at B and charge at A. So the direction of the forces have been marked as FCD, means force on charge at C due to D, force on charge due to charge at B, force on charge C due to charge at A. So we can calculate force on charge C due to charge at D, K Q1 Q2 upon the square of the distance, and that is A square. So finally it is K Q square upon A square. Similarly, I can calculate what would be the force on charge at C due to charge at B, and that also comes out as K Q square upon A square. Finally, we need to calculate what would be the force on charge C due to charge at A. Diagonal, the distance is root 2a. So the force would be K Q Q upon root 2a ka whole square, and that gives me K Q square upon 2a square. Now I need to calculate what is the resultant force on the charge at C due to the charges that have been placed at points B and D. So using, I can calculate FC, charge or force on charge C due to charges at B and D respectively. It would be FCD ka square plus FCB ka square plus twice FCB CD cos pi by 2. And what is the value of cos pi by 2? 0. So I can write it as KQ square upon A square under root of 1 plus 1. So the net force is having a magnitude root 2 KQ ka square upon A square. Then I need to calculate what would be the direction of FCB plus D. For that, we mark here an angle alpha and calculate what would be the value of tangent alpha. So tangent alpha would be given by force CD upon force CB. The two forces are equal in magnitude, so ratio comes out to be 1. And 1 is the value of tangent 45. So what is the value of angle alpha? Alpha is equal to pi by 4. that is, it is also along the diagonal. So the two forces that are left are FCA and FCB plus D, which are both along the diagonal. So the net force would be equal to KQ square upon 2A square plus root 2 KQ square upon A square. Then the net force would be given by KQ square upon 2A square root 2 plus 1. So that is how we utilize the superposition principle to calculate the net force. Now, we are about to study the concept of continuous charge distribution. Why do we require it? Because the concept of quantization of a charge holds only at microscopic level. When the size of the charge distribution becomes important and the magnitude of the charge becomes large, then the concept of continuous charge distribution is utilized. So what do we mean? Where are we supposed to use the concept of continuous charge distribution? When the size of the charge has become large. And secondly, the magnitude of the charge also has become large. Because quantization concept was used for independent discrete charges only. We have three types of continuous charge distribution: line charge, surface charge and volume charge. Here the most important word to describe them is charge density, and while talking about charge density we ignore the concept of quantization of charge and the concept of discontinuity in charge distribution at microscopic level. Why? At microscopic level the charge distribution is discontinuous because there are discrete charges which are separated by intervening space, and at those spaces we do not have any charge. The first type of charge distribution that we talk about is the line charge distribution. What does it say? When the charge is uniformly distributed along the length of a conductor, then it is called line charge distribution. We have a line charge here. We choose a very small element of length delta L. That length carries a charge delta Q. We all have a point of observation P at a distance R from point O. Now, delta L already said small element of length, delta Q charge on this element of length delta L. How do we define line charge density? We represent it as by lambda and is equal to delta Q by delta L. The line charge density is ignoring the concept of quantization of charge as already said, and discontinuity in the charge distribution. Lambda, what does it represent? Macroscopic line charge density, which is a smoothed out average of microscopic charge density in a length element delta L. Remember, delta L is microscopically large, but macroscopically it is very small. How do we define lambda? We define it as charge per unit length. How do we calculate total charge? It is calculated by the line integration of delta Q, that is lambda times dl. How do we get lambda times dl? From this equation here, delta Q would be equal to lambda times dl. What is the unit of line charge density? Coulomb per meter is the line charge density. What would be the dimension? L minus 1 T1 ampere power 1. And what would be the electric field? It would be given by K, the total charge, upon R square. The second type of charge distribution that we talk about is called as surface charge distribution. So we have a sheet of charge here, and the entire area is divided into small areas delta S, and each delta S carries a charge delta Q. Again, we have a point P, point of observation, at a distance R from the origin O. How do we think of surface charge distribution? when the charge distribution is distributed along the surface area, then it is called as surface charge distribution. What is delta S? A small element of area. And what is delta Q? Charge on element of area delta S. Now, surface charge density sigma is defined as delta Q upon delta S. It is defined as charge per unit area. How do we calculate total charge? As the surface integration of delta Q. Surface integration sigma times delta S. What can be the possible unit? It can be coulomb per meter square and dimension L power minus 2 T power 1 ampere power 1. What would be the electric field? As usual, it would be K times the total charge upon R square. Now, once again we must remember here, the surface charge density sigma ignores the concept of quantization of charge and discontinuity in the charge distribution. For the same reason, sigma represents macroscopic surface charge density, which is nothing but a smoothed out average of microscopic charge density in an area of element delta S. Third type of charge distribution is the volume charge distribution. Here each represents a small volume delta V carrying a charge delta Q. From the point O, we consider a point P here at a distance R. How do we define volume charge distribution? When the charge is uniformly distributed throughout the volume, then it is called as volume charge distribution. So, what does delta V represent? It represents a small element of volume. What does delta Q represent? Charge on element of volume delta V. How do we define volume charge density? It is defined by rho and it is delta Q by delta V. Volume charge density is defined as charge per unit volume. So, line charge density, charge per unit length, surface charge density, charge per unit area, and volume charge density, charge per unit volume. The total charge, as usual, it was first line integration, surface integration, and now the total charge is volume integration of delta Q. So, volume integration rho times delta V. What is the unit of volume charge density? Coulomb per meter cube. What are the dimensions? L power minus 3 T power 1 ampere power 1. As usual, the electric field is given by K times the total charge upon R square. Here rho also represents macroscopic volume charge density, which is nothing but a smoothed out average of microscopic charge density in an area element delta V. So, the basic concepts remain same. We have three types of continuous charge distribution: line, surface and volume, representing one-dimensional, two-dimensional and three-dimensional nature of charge distributions. Thank you all. Hope to see you soon.